Welcome back to our course on networks and distributed systems. This would be lesson 6. In the last lecture, we talked about packet switching technology. So let's pick up from there. The other technology we're going to discuss is circuit switch networks. In a circuit switch network, the resources needed along a path to provide for communication between the end systems are reserved for the duration of the communication session between those end systems. The circuit switching approach is used when you make a phone call. When you dial your phone, all of the connections between you and the person you're calling are established. You own that circuit for the duration of the call. When the network establishes the circuit in data communication, it also reserves a constant transmission rate in the network's links for the duration of the connection. Since a given transmission rate has been reserved for this sender to receiver connection, the sender can transfer data to the receiver at a guaranteed constant rate. When two hosts want to communicate, the network establishes a dedicated end-to-end connection between those two hosts. Consider what happens when one host wants to send a packet to another host over a packet switch network, such as the internet. As with circuit switching, the packet is transmitted over a series of communication links. But different from circuit switching, the packet is sent into the network without reserving any link resources whatsoever. If one of your links is congested because other packets need to be transmitted over the link at the same time, then the packet will have to wait in a buffer at the sending side of the transmission link and suffer a delay. The internet makes a best effort to deliver packets in a timely manner, but it does not guarantee anything. A circuit in a link is implemented with either frequency division multiplexing, abbreviated FDM, or time division multiplexing, TDM. With frequency division multiplexing, the frequency spectrum of a link is divided up among the connections established across the link. The link dedicates a frequency band to each connection for the duration of the connection. For a time division multiplexing link, time is divided into frames of fixed duration, and each frame is divided into a fixed number of time slots, as you can see here. When the network establishes a connection across a link, the network dedicates one time slot in every frame to this connection. These slots are dedicated for the sole use of that connection, with one time slot available for use in every frame to transmit the connection's data. Proponents of packet switching have always argued that circuit switching is wasteful because the dedicated circuits are idle during silent periods. With frequency division multiplexing, each circuit continuously gets a fraction of the bandwidth. With time division multiplexing, each circuit gets all the bandwidth periodically during brief periods of time. Establishing end-to-end circuits and reserving end-to-end transmission capacity when using a circuit switch approach is complicated and requires a complex signal software to coordinate the operation of the switches along the end-to-end path. Critics of packet switching have argued that packet switching is not suitable for real-time services, such as telephone calls and video conference calls, because of its variable and unpredictable end-to-end delays. Proponents of packet switching argue that it offers better sharing of transmission capacity than circuit switching, and it is simpler, more efficient, and less costly to implement than circuit switching. In a packet switched environment, the link is only unavailable to others when it is actually in use. In other words, when one is browsing a website and takes a moment to go to some other room, the links are completely free and available to other systems. In a circuit switched environment, if the user stops for whatever reason, the links are still reserved and unavailable to other systems. Think for a moment about the issues around frequency division multiplexing and time division multiplexing used by circuit switching technology. Each user gets a share of the bandwidth, whether it's a share of time or a share of frequency. Let's say that the existing bandwidth is being shared by 10 hosts. If one of the hosts needs to transmit a great deal of data and the other 9 are idle, the one host still only has access to 1/10 of the bandwidth. The rest of the bandwidth remains idle. That problem does not exist in a packet switching environment. Packet switching allocates link use on demand. Link transmission capacity will be shared on a packet-by-packet basis only among those users who have packets that need to be transmitted over the link. All this is not to suggest that there are no problems with packet switching. This technology is great when there are occasional large demands for some hosts while others require little or no bandwidth. On the other hand, if there are many large demands for bandwidth among the hosts, there can be network congestion where packet loss or delay can be a problem. Because of this, there must be protocols in place to control congestion and traffic flow. Such protocols are unnecessary in a circuit switching system. Packet switching, however, is simple and requires little time to set up. A significant issue with circuit switching is that setting up the circuit is time consuming, and time is also needed to take the circuit down after use. Also, if the circuit is broken during transmission, the entire setup must be done again. Let's take a break now and take care of any assignments you have pending, and when you're ready to come on back and we'll go to lesson 7.